Welcome. In this video, we will demystify how rays are sampled within NeRF within NeRF pipelines. That's a video that I've been asked a lot. Because in my video I usually try to make to remove all those complexities from sampling rays by pre-computing them. So in this video we'll see how they are generated, and therefore you'll be able to generate your own rays with your own dataset. Once you've generated your rays, you can just shoot them in the scene and then do the NeRF rendering or the volumetric rendering. So once you have your rays, that's very easy, but generating those rays can add a bit of friction, yet it's not complicated. So we'll really have a look at how it's done. All that content comes from my course about NeRF. I will put the link in the description if you're interested and if you want to learn more about rendering on board NeRF. But otherwise, let's dive in. So here, for example, we have a camera that is looking at an object, at a fox. Let's call that a scene. So we have a camera that's looking at a scene and that will generate an image. We have this red point. Let's call that the camera coordinate center that we see here. With this coordinate center, this is the coordinate center in the camera world. The camera will shoot rays in the scene. And then for each ray, each ray will represent a pixel. And the question we want to ask is what is the color that each ray will see in the scene? What is the color of each ray? Okay, so here we have our image plane. So basically, this is our image. Let's say it is the 8 is h, so the number of pixels, the resolution for the 8. W is the width. Let's use a conventional coordinate coordinate system for the image. So we have the x and y coordinates for the pixels. That's all. Okay, here it's a bit different than in Python. So in Python, first we'll query the row and then the column. Here, usually in image processing, that's the opposite. First we have the first coordinate. It's a column and then the row. So you need to be careful about conventions. Everything we see here, we will choose a convention. We'll come back to that in a moment. But if you choose other conventions and you adapt your equations accordingly, that's fine as well. It's all a function of conventions. So here we say, okay, this is u, this is my x coordinate for the pixels on y or on v. And therefore, for given pixels u, v, we want to compute the direction of that ray. Let's for example have a look at x. So if we choose this convention for the camera coordinate system, so x that points in that direction, y in that direction, and z in that direction, we will come back to that in a moment. That's a right-handed coordinate system. I will explain why that's so important. So for example, if we try to map u to x, to compute the coordinate transform to move from one frame to the other one, we can easily see that x is equal to u minus w divided by 2. Because x is z, we can see the projection of z. The z-axis, it's called the optical axis. It goes through the middle of the image, here in the center. On x, it goes in the same direction as u. So for example, but it's offsetted by the width of the image divided by 2. So for example, if u it's equal to w divided by 2, so we are on that point, then x is equal to 0. That's very easy to do the math. So we have x equal to u minus w divided by 2. Let's say that u is equal to w, we are at that point, then x is equal to w divided by 2. For y, this is the opposite. Well, this is the same equation in terms of offset, but then we need to multiply everything by -1 because u and v are going in different direction. I could have chosen, for example, to put y pointing downwards. That's just, again, a convention choice. And then I will not have had to add this minus here. But here, because y points upwards, I have this minus sign. And then the last thing is z. Z is equal to minus f. So what is f? F is the focal length of the camera. We'll come back to that in a moment. So basically, the distance between the image plane and the camera coordinate system is f. That's called the focal length of the camera. That's where everything will focus. So yeah, basically here we're modeling a pinhole camera on the distance between the image plane on the pinhole on the camera coordinate system is f. Because z is going in that direction, on the image plane is in between the object on the camera, the z coordinate is equal to minus f. Okay, so I will come back in a moment to why z is pointing in that direction. For example, if z was pointing in the other direction, we would have had z equal to f instead of minus f. But maybe let's come back to what is f. So for example, we can come here in Blender. So this is what you will see if you just open a new scene in Blender. On my camera, I have multiple parameters for defining my camera. Of course, we have the height and the width of the image. We've already talked about that. And we also have the focal length. So here by default, I have a focal length of 50 mm. And for example, here I can render an image. And this is what we see. So we have a look at this object. And now let's modify a bit the focal length to see what will be the impact on the image. You can also have a look at this 3D object, the camera. You see that if I modify the focal length, I modify the distance between my image plane on my camera central. On that we'll also have a look on the image. I'm zooming a bit. So if I keep the camera in the same place and I'm modifying the focal length, I will zoom a bit on my object. Okay, and let's do the opposite, maybe 25, and then it will do the opposite. You see now that the image plane is going much closer to the camera coordinate center, and then I can render an image. And now we are zooming out. And basically, this is what you do when you play with when you have a camera, and you are turning like you are playing on the lens by rotating it. You are modifying the focal length to zoom in or zoom out. So yeah, on professional photographers, they have different lengths that they plug on the camera, and therefore they play with those kind of parameters depending on the scene they want to capture. So the last thing, so basically we've explained this equation. Maybe a last thing is z is pointing in that direction because here we have a right-handed coordinate system. That's up to you if you want to work with a left or right-handed coordinate system. So the first choice to do is to choose x and y. So here I've made my choice. X is pointing in that direction, y in that direction. And then I need to choose z. So if I choose a right-handed coordinate system, z should point in that direction. If I had chosen a left-handed coordinate system, z could have pointed in the opposite direction. Here I'm choosing right-handed coordinate system because I used Blender to generate my camera parameters for my cameras, generating the rotation. I use Blender to get the coordinates of my camera. On Blender uses the right-handed coordinate system. So that's very important that I choose the same convention. If you are working with OpenGL, it's also right-handed coordinate system. So you need to be very careful with all the tools you use about the conventions, about the coordinate system, on if it's a right-handed, left-handed. Again, it's just a matter of convention. You use any coordinate system you want, but then you want to make sure that you use the same for all your tools, or that you use some transform matrix to correct to move from one coordinate system to the other. Let's say I had generated all my camera parameters with some software that use other convention. Then before plugging those parameters into my NeRF pipeline, I need to do some conversion to go from one coordinate system to the other. But okay, let's move on. Let's work with that coordinate system. So we've said that we're working with those equations. So we know that our camera has three main parameters with this model, at least: the height, the width, and the focal length. So maybe I can create a function, get rays, to get rays from my camera. I can define the height of the camera, the width of the camera, and then the focal length. The focal length, let's say, in all generality, that it's a float. So let's compute a for now, let's say that the origin of the ray is just 0 everywhere. So np dot zeros of 3. So basically, this is my origin. This is the center of my coordinate system for the camera. Let's say it's in 0, 0, 0. And then we can compute the direction of this ray. So going from 0, 0 to uv, we've seen that if we want to go to uv, along the x direction, I should move by u minus w divided by 2. Along y, I should move by this quantity. And along z, I should go in the opposite direction by a factor of f. So I can create the direction of my ray. Direction is equal to np.array. And then, so we have, if I recall correctly, u minus w divided by 2. Then for y, this is the same equation, but we need to invert it because it's pointing in the opposite direction as v. So here we have minus. And then for z, it's the minus focal length. Okay, great. And then we can return the origin and the direction. So this is for a single for a single ray that is a given coordinate u and v. But here with this get ray function, we don't want to do that for a single u and v. What we want to do is to compute all rays at the same time. So we want to compute all the rays for all u's and all v's. So the first thing we are going to do is to compute this grid of all u and v coordinates. And when this is done, we are going to compute x, y, z for all rays at the same time. So we're just going to generalize those equations to make them work for all the rays. So maybe we can start by creating u and v. So for example, we can say uv is equal to np.meshGrid. I'm creating a grid. So along the u axis with np.linspace, we go up to w. I think it's better to use np.orange. I think with linspace we will need to add more extra parameters to get the same functionality as just np.orange. And then np.orange h. So basically what we're doing, let's say for example np.orangew, we're creating this row. We're doing the same for v, we're creating this column, and then we're creating the mesh grid to compute the intersection of all of them, and then we get our grid. So once this is done, so now we have our coordinates u and v. The shape is something like for each it's like a shape of h, w. So here we will reshape them. So u is equal to np.reshape u. For example something. No, let's do that. -1, 1. So basically now the shape will be h times w, 1. Or we can even remove this 1. Let's just do reshape -1. And let's modify the d type as well. Let's do s type np.float 32. I think by default it might be 64 by default. But just to make sure, let's do that. Let's do the same for v. So we reshape them so that they are a one row array rather than a 2D array. And once we've done that, then we can compute d for all the rays. So now u minus w divided by 2 is no longer a single value. It's an array. So here, instead of doing np.array, let's say np.stack. Okay, and we should be fine. Let's mention along which axis we want to do the stacking. So let's say axis is equal to -1. We want to stack along the last dimension. Here let's give a list, a tuple instead of a list. Let's try that. Let's see if it's working fine. Get rays. Let's say we want an image of 400 by 400 pixels, and let's use a focal length of 1200. We have an issue. NP is not defined. Let me run everything. import numpy is np, of course. Reshape. Oh, okay. So I see. We don't want to call that on np, but on u, on v. We want to call that directly on the object. So let's run that. We have an extra issue. Okay. The issue is that here the shape of that is h times w. The shape of that is h times w as well, but this is just a scalar value. So let's do, for example, np dot once like u times f. So by doing that, we are creating a tensor that is the same shape as u, and that is minus f minus focal length everywhere. Now we should be fine. Okay, that's working fine. On one side with the origin, on the other side with the direction. So let's do that. Raise origin, raise direction is equal to get raise. And let's have a look at the shape of raise direction. If everything was fine, we should have 400 by 400. So this h times w, comma 3, because it's a 3D tensor. We're in a 3D coordinate system. Okay, we're fine. 400 by 400, comma 3. The issue is we don't have that with the origin. If we print the origin shape, for now it's just 1, comma 3, because the origin is the same for all rays. But for consistency, we want the origin with the same shape as the direction. So maybe let's say origin is equal to np.tile, the origin, comma, raise direction dot shape, comma 1. So basically that means we are repeating the origin vector by this amount, so 400 by 400. Okay, and now they have the same shape, that's fine. Okay, so now we have a function that is able to shoot rays from the camera to the world, and basically then we can query the scene to ask what will be the color of each ray. So either we can use standard approach such as path tracing to get the color of each ray. We can use volumetric rendering either with NeRF or without NeRF. And yeah, so now with our rays, last thing to do is that D should be a normalized vector. For now D is not normalized, but in ray tracing, in physically based rendering, we are working with normalized direction vector. Why? Because if I want to know what is the position of the vector after a given time t, so basically the equation would be O plus t times d. So I want to know where is my 3D vector after t time step. In order to be able to compute this equation, or for this equation to make sense, I need d to be a normalized vector. So last thing to do, we can normalize d before returning it. So let's say direction is equal to direction divided by np dot linalg dot norm. So we're normalizing over the last dimension. So where we have the three values, and we can also say keep dims is equal to true. So this is to keep the same dimension as d. If we do not put this argument, we will only have a 1D tensor. Here by saying keep dimension is equal to true, we keep the 3D, well the 2D tensors where the last dimension is 3D with 3 values. So basically the norm for all those 3 values are the same, but that allows to do the division like this because the two arrays have the same shape. If we do not do that, we will be unable to do the division. We will have some issues with the shapes. So if we do that, that should be fine. Let's very quickly compute the norm of the direction to make sure it's fine. So let's say ray direction to the square, and then we take the sum along the last dimension. So basically here we are doing in a vectorized form x squared plus y squared plus z squared. and that should be equal to 1 everywhere. Okay, so we see it's roughly equal to 1, of course with some numerical instabilities, but with a normalized direction vector. So let's create an image very quickly to see the impact of that. So here I have a sphere. Let's create a sphere. So let's say sphere is equal to sphere. So I will not go into the detail of that. That's better explained in my Udemy course. But basically, let's say this is a scene. So this is modeling my object, and I will send all those rays to the scene, and I will query what are the values of each ray, and therefore I can produce an image. So my camera is in 0, 0, 0. Z is pointing in that direction. So in order to see the object, for example, I can put the object in Z is equal to -1. If I put Z in the positive Z direction, it will be on that side, and I will not see the object. But for example, if Z here is equal to 0, here Z is equal to -1, I will see the object. So the sphere it's taking as input. So let me take my cheat sheet. So it's taking as input first a NumPy array. So I think the first thing is the position of the object. So let's say 0, 0 on -1. Then it's taking the radius of the sphere. Let's say 0.1 for now. And then it's taking the color of the sphere. So let's say np.array. And let's put a red color. So RGB, R is equal to 0. G on B, so the green and blue values to 0. So it will be a red sphere. Okay. So okay, let's have a look at our sphere script. PRC, okay, that should be fine. What is the issue here? Okay, that's an issue with array. Okay, I forgot to do that. On here we might have an extra parenthesis. Okay. So I've created my sphere, and I can call this intersect function. Here I will not go into the details of that because that's not the purpose of this video. Here we will really focus on the rays. So here that's doing basically rendering, but based on surface intersection. That's described in my course. But here we basically what really interests us is the rays and also volumetric rendering. So basically all that, this is what you will do with NeRF. You would send your rays to NeRF and ask the NeRF, okay, if I intersect my NeRF model with those rays, what is the color I get for each ray? So if you are familiar with NeRF, you've already done that, maybe with a different form, with a different API. But this is what we do when we do NeRF. So okay, so I'm sending my rays in the scene. I'm querying the rays. I'm intersecting the rays with the sphere, and therefore I will get the color of each ray. Let's have a look at the image.shape. So basically this is the same shape as the rays. So let's reshape it as an image. So we know that with 400 by 400 pixels, and that with three color channel. And then let's plot the results. plt.emShow. Let's show the image. Okay, and therefore we see our sphere. What we can do is to modify, for example, the radius of the sphere. If we do that, we see okay that the image changes. So basically here I'm defining a 3D object, and we see that when I modify the 3D object, the images changes as we expected. So yeah, that's pretty nice. Let's do maybe something else. Let's push the sphere away from the camera. So instead of doing -1, let's do -5. And we see that the sphere, we see it moving away from the camera. We can do the -0.5, for example, to put it closer to the camera, and we see that the sphere is coming closer to the camera. So okay, with everything as expected. Now let's do something else. For example, we know that in this coordinate system, y is pointing upwards. So that means that if I take my object, I move it in the right, in the y direction. in the image, the object should also move up. It should move up. If I move it in the x direction, the object should move to the right. So let's do this quick test. So here my sphere, let's move it in the x direction. Okay, so that was maybe a bit too much. It was not okay. So we see that if I move in the x direction, it's moving to the right as expected. If I move it in the y direction, it's moving up as expected. Now let's say that I had chosen a different coordinate system, so that I had chosen that y will be pointing downwards. So let's do that very quickly. So here I remove the minus, so I'm choosing that y is pointing downwards. So now that means that when I am moving the sphere in the y direction, it will move down in my image. So that means that now my object is exactly at the same place as my previous image. The object is exactly at the same space, but at the same coordinate, but the image is different just because I've chosen a different coordinate system. So that's very important that you, let's say you are in a lab, you know the position of your object. If you use one coordinate system or the other, your image will look different, and therefore you might not get the results you expect. So it's very important to understand your coordinate system, or you chose a coordinate system when you took your measurement, on which tools you used, on which coordinate system are used from your tools. So let's come back to the coordinate systems from the slide, this one, and let's come back to that. Okay, and now we can put back the sphere in the center, like this. Okay, great, perfect. So we are almost done with the rays. The last thing, you see by the end it's very simple. It's only a few equations. The last thing we need, it's only a few lines of code on a few equations. The last thing we need to do is to add the camera toward matrix, because this is in the camera coordinate system. But if you want to rotate your camera and to put it in some to offset it with respect to the world coordinate center, you might want to rotate your camera and to translate it. So to do that, we'll add the camera toward matrix. Maybe before that, we can very quickly plot a function to visualize the rays. So for example, let's do def plot rays. We can take as input the origin and the direction of the rays. Those are NumPy arrays. Okay, great. So this is done. Then we can create a figure. Figure is equal plt.figure. Figure size is equal to 12,12. Okay, great. We can create a 3D figure. So let's project that into some 3D axis. So plt.figure, plt.axis projection is equal to 3D. For now, let's just do a quick test because I know that there was some refactoring of Matplotlib, so I want to make sure that this will work. So plt.show on, let's say, plot rays with our rays origin on rays direction. Okay, perfect. It's working fine. Now let's add the rays. Here we might have a lot of rays, so let's maybe generate new rays, but with a lower resolution. So instead of doing 400 by 400, that means we need to plot a lot of rays. Let's just do 20 by 20. So we only need to plot 400 rays. So let's say point 1, so basically this is the origin. This is where the ray is at the beginning. On point 2 is equal to origin plus t times d. We can say t is equal to 1 by default. This is a hyperparameter. And basically we'll plot where the rays are after t time steps. And now we can plot each point. So we can say for p1, p2 in zip, pt1, pt2, plt.plot p1, p2, and we can say c, the color is equal to c0, so that we have the same color for all rays. yeah, here we're in 3D, so basically here it's a bit different. So we need to say the x coordinates of the first and second point, the y coordinate, and the z coordinate. So basically here we will have p1 of 0 and p2 of 0. So basically this is the x coordinate of the beginning of the line, and this is the x coordinate at the end of the line. And we can do the same for y and z. And that should be fine. Let's do a quick test. Okay, so they don't have the same shape. So okay, so here we're using origin direction. So we have some issues with shape. So it seems that D does not have the right shape. Where is origin? Where is that? Let's plot the shape of the data. Print O.shape, D.shape. Okay, here they have okay, so now it seems fine. I don't know what happened. Maybe I forgot to recompile the function. On here we're seeing those rays coming from the camera to the scene. We see the results after one time step. Let's say that we say now t is equal to 10. We see that the rays have traveled much more if we have a look at the z-axis. So we see where the rays are after 10 seconds, and we can make very nice animation. For example, we can plot little by little the rays propagating, and then make a video out of it. Just with Matplotlib or with those kind of functions, you can make very nice animations. Okay, so basically, one last thing is that you might see that you don't see what you would expect from the slide. So from the slide, you would expect the rays going in that direction to the left. Here it's because Matplotlib, using a coordinate system where z is pointing upwards, x and y are in this plane. So again, it's all a function of coordinate system. With Matplotlib, z is pointing upwards, but we see that our rays are going in the opposite direction of z as expected. Okay, so last thing, and then we'll be done with this video. We can incorporate the camera toward the matrix. So let's say camera toward 1 is equal to np.load c2 camera toward 1.npy. So I have already prepared and generated those camera toward matrix coming from Blender, but you can use your camera toward matrix either coming from some tools like Blender, coming from Colmap, coming from NeRF Studio. Once you have a camera tool matrix, you can generate your rays. And then let's modify this function getRays. Now the getRays function will take as input a camera toward matrix that will be a npy.array. And basically the thing is that the camera tool matrix is a 4x4 matrix. Okay, we can just print it. Here we have the rotation. The first 3x3 matrix is the rotation of the camera. The last column, the first three values of the last column, this is the position of the camera. So basically here, the origin, instead of being 0, that will be the camera toward matrix. That will be the last column. So the first rows, the first three rows, the first three values on the last column. So now this is our origin. Our camera is this position. And then D, what we need to do before doing the normalization, we want to do a coordinate transform. We want to move from one coordinate system to the other one by doing a rotation. So basically, it's very simple. We just do a matrix multiplication. So D is equal to C2W. We are taking the first 3x3 matrix, so the first three rows on the first three columns, because we want this part of the matrix that represents the rotation. And we do a matrix multiplication with D, and we'll need to do some squeezing. So we need to add the last dimension. It's just to make sure that in terms of dimension, we are fine. So basically, we'll have something like this, something that is 3x3, and we are doing a matrix multiplication with something that is n times 3 times 1. And therefore, once we have those dimensions, this operator from from NumPy, the matrix multiplication, the multiple operation, will do n times the 3x3 multiplied, well, matrix multiplied with the 3x1. And then the result will be 10 times 3 times 1 result, and therefore you get 10 times. So the batch size in some way a 3D tensor. And then we can remove this last dimension. So we will go from n3 1 to n3. So we can just squeeze the results, dot squeeze -1. Let's try that. Let's get our arrays and make sure. Okay, we can do that maybe to test it. I can delete that. Let's call get arrays with camera 2 old matrix 1. And we see now that our arrays are, that the camera is offsetted, and we see that the arrays, maybe if we remove t, if we t is equal to 0.1, maybe that will zoom in a bit. But we see that the camera is being rotated. Okay, that does not change much. Okay, so now let's remove that, and let's query again our sphere. So basically here, this camera tool matrix is rotating around the origin. That's the setup used in most neurosynthetic scenes. So now let's put a sphere in the center of the scene. I think we can increase a bit the radius. Let me double check. Yeah, we can use 1, for example, because the camera is far away, and then we can render the sphere. Okay. And we can show the results. Okay, we have again some issues with the shape. I'm not sure I understand what's happening, so let's have a look at raise origin and resurrection.shape. I think it's one of my variables, it's maybe not properly named. Okay, so the raise origin is not properly named. So, okay, yeah, here I'm using raise direction, but it should be D. In this script we're using D, but not raise direction. Okay, so here we can rotate the camera a lot. We'll not really see the difference because we have a single sphere, and from every viewpoint it's the same sphere. So maybe let's create a scene with 2 spheres. So you have 1 sphere in the middle. Let's create another sphere that is offsetted, maybe by 0.6 and 0.6 in each direction. Oh yeah, here let's do plus equal. So basically I'm rendering the first sphere, and then on top of that I'm adding the results of rendering the second sphere. Okay, on here we're seeing those 2 spheres side by side. And now instead of using camera tool 1, camera tool matrix 1, let's use camera tool matrix 2. And therefore we'll see that we are rotating around those 2 spheres. Camera tool matrix 2. Okay, so here you see with 1 camera tool matrix. So here the spheres are in the same place in the center of the scene, and then with respect to where your camera is, you are seeing different. You are seeing the spheres from different perspective, and therefore we are able to rotate around those spheres. And therefore you can play with the camera tool matrix, create a path where the cameras are rotating around the object, and then you can make GIF, you can make MP4s, you can make great videos. Yeah, so that concludes this video. So you can see that once you have your camera tool matrix, once you have the camera parameters, the height, the width, and the focal length, it's very easy to generate your arrays. And therefore now you can start from any tool you want, from Blender, OpenGL. You can use Colmap to get real world camera tool matrix from your images, and then you can just plug them into that function. Again, be careful about the coordinate system, and you can get your arrays and then plug them into any NeRF pipeline, any reconstruction algorithm, and for example the one we've seen in that in my previous videos. So I really hope this video was helpful to you. If it was, please leave the thumbs up, it really helps. And don't forget to subscribe for more content like that.